and those interesting features about Mathematica, but at the end of the day, I think it's all about another option to the pencil code users. And for me personally, I started to use this because by the time I started to use the pencil code, I was more familiar with Mathematica compared with Python or IDL. So I'm just playing with the code and trying to see if I can use Mathematica, and turns out to be to formulate as a package. So let me get into the stuff here. So the package comes with the pencil code. If you download it from GitHub, so this is the pencil code GitHub page, and it's right in the pencil code folder. So it's should be in everyone's folder. And there's some online materials about the package. If you go to the README here, documentation, and there is this link here. And on the left, you see all those tutorials, and there is this Mathematica tutorial, which essentially covers almost everything I'm going to say today. So the first step is to load the package. So essentially, you go to a. So I would assume you have some basic knowledge about Mathematica, like symbolic computations and so on. And yes, so basically you type this first line in your Mathematica notebook, or if you're on a supercomputer, you type it in the command line. It's like this, and this will identify the initialization file of Mathematica, and you edit this file. So is the font okay here? Is it large enough?
Yeah, maybe slightly. Yeah, I think it's okay.
Yeah. So I'm saying I'm going to edit this file. And I add this line, append to path, and the path to the Mathematica package, and that's it. You only need to do that for one time, and then each time you load the Mathematica kernel, it will identify this package. So that's all you need to do. Then after doing that, you say needs PC dot. So this is the grave key to the left to the number 1 on your keyboard. And this is something like a namespace. It's called context in Mathematica. So you will need this dot here. So you say PC dot, and you say PC initial, that's it. Then the package is loaded. So then before I go to specific comments, I want to introduce this book. So it's this one here. So this guy, this author, I think he graduated as a physics PhD and then become hired by the Wolfram company or so. So this book is totally free, written by him, and I think it's a very nice introduction to Mathematica if you want to write efficient programs. Okay, so now going to dealing with pencil code data. So first I define a string, which is the director of my simulation. So first command is called get param. So this will, it reads some basic information from the simulation, but also computes Reynolds numbers, for example, which requires the need to read some other, for example, the RMS velocity in the time series, and then do some post-processing. So for example, an x is the grid number in the x direction. I can compute Reynolds number, I can compute editorial time, and so on. So for each function, you can type question mark and then followed by the command self to extract the help information. So if I do this, you get some help information, and The next thing I'm going to introduce is reading the time series, and you can do the read TS and shows input, output, and so on. So next, reading the time series. So the basic syntax is read TS, sim, and then following a string, which is the column you need to read. For example, I want to read the time, and it returns a list. Basically, so if I show you the directory, so this is the time series of the run. Basically, I'm extracting this second column here, and it returns as a list. I can extract multiple columns at the same time if I also want the RMS velocity, and I also want the RMS magnetic field. I do this, and it returns a nested list, which contains 3 sublists corresponding to those 3 columns. So what I can do is I assign the value to 3 variables like this, and then I can plot. So like this, if I'm going to plot the RMS velocity, and I can also specify the scaling functions. For example, I'm saying the horizontal axis, I don't want a rescale, but I want the vertical axis to be in log scale. You can also say signed log, which is a signed log scaling. And all those are like built-in functions of Mathematica. The next is to read 1D data. By 1D data, I mean the following. So if I look at the, say, the power spectrum of the velocity field, it's something like this. So the first line is the time. Second line is the spectrum. So here the resolution is 8 by 16 by 8 by 16 by 30, 12. Strictly speaking, I shouldn't compute power spectrum here, but anyway, we should have 4 columns here, which is 8 by 2, which is written in 1 line. If you have 512, say, resolution, then it will be like 256 columns in the second line. Then the third line is again the time, and the fourth line is the data, and so on. So by 1D data, I mean any data file which is structured in this way, like time and data one line by one line. Which means this reading procedure not only applies to power spectra, but also plane averaged fields, like XY averaged magnetic field, and so on. Right, so let me show you how to do this. So here I'm using another run directory, which is I think 16 by 16 by 16 MHD simulation. So an alpha squared dynamo. Right, so the second line here, I'm just plotting the time series. RMS velocity, BMX, B1, the YZ averaged field, the XZ averaged field, and XY averaged field. So in this case, the dominant one is the second, the XZ averaged magnetic field. So then I want to read, for example, the magnetic energy spectrum. So the syntax is read 1D, and followed by the file you want to read. So in this case, we want to read power.mag.dat. So it returns, again, a nested list. The first list is all the time, here, 1 to 15. And then the second element is again a nested list, which contains the power spectra at different times. So this is power spectra at the first time. This is power spectra at the second time, and so on. So what I can do is I say time spectrum equals this. And then I can plot, let's say we want to plot the power spectrum at t equals 15. So I want to extract the last element like this on a log scale. I guess it's because the resolution is too low, so you are seeing some very unphysical power spectrum. But
why does this have 4 elements? This power spectra 4 for each
I
time?
guess
With different
I
values?
think it's because it's 8 by 8 by 8 resolution. So we can check. So it's 16. Now I'm not sure. Right, I see. I should say sim2. Now it's correct. So now it's 8 columns. Right. So okay, so now this is now it has 8 columns. You can also read planar averaged fields. For example, here I'm reading the XY averaged field, BX means Z. So this you have to write in XY average.in file. And again, if you call this command, it returns something huge, but basically the structure is similar to the power spectrum. For the time, you have all the times. And for this variable, you have a nested list. This means you have 1,200 time snapshots, and for each you have 16 columns, corresponding to 16 grids in the Z direction. So if I plot this, you can see this is the XY average field in the Z direction. Sorry, the Z profile of this field. And there's also a convenient command called space-time diagram. So you can quickly plot those butterfly diagrams from the simulation. Right. Then about reading video files or slice files. So those are under the name of something.xy, xz, or yz. So the basic syntax is read slice sim followed by which slice. Sorry, now I forgot the syntax, so I have to check that. Okay. So following the second argument is the variable. Let's say we want to read BB1, sorry, the UU1, let's say, the x component of the velocity field, and followed by the slice, let's say the XY slice. So it returns a nested list again. Actually, it has 3 elements. The first is time. Sorry, the first is the slice, which are like 2D matrices at different times. The second one is time. The third one is the position of this slice. So for example, the slices, you have 31 snapshots. And why this? Because this simulation is 8 by 16 by 32, which means if you read the XY plane, it will be 16 by 8. So 16 by 8 is x by y, sorry, y by x, and 31 is the numbers of snapshots. The position is basically where this slice is. So this means the slice is at z equals 24, which is 8 pi. Right. So then you can actually make density plots of those slices. Say, for example, I want to do list a density plot. I want to plot the last slice. So I say -1, showing something like this. I can make aspect ratio equals to 2. Yeah, And you can make plots of every slice and then make a video file out of it. So then you can use this command. The /add simply means I want to apply this function to each element of slice. So if I do this, then frames, this variable, actually is a list of plots. For example, its first element is a plot, second element is also a plot, and so on. So then I can do a list animate of all those frames. And it will create a animation of all the slices. Another example here is I first use a loop to read the x, y, y, z, and x, z slices of the x component of the velocity field. Then there is this command called make boxes, which renders a box given those three surfaces of the box. So I do this. It takes some time. And this error, I'm not sure, it's some Mathematica thing. If I reboot Mathematica, it will go away. So now, okay, so frames now is 31 frames of boxes. So the first element, let's see, is some box and so on. So again, I can make a animation of all those frames like this. And of course, you can export all the frames into a video file, and you can specify the frame rate. Takes some time to do. And if I now that's just okay, never mind. Right. And now if I right, this is the generated video file. And you just have a video. And all those like frame ticks and labels, those you can change by hand. Okay, now reading the var files. So first there's this unsnap. By the way, how much time I have?
You have some time, maybe around 10 to 15 minutes.
Okay, I'll be quick. So the nsnap basically returns how many snapshots, var files you have. So in this case, 100 and so. The basic syntax of reading a var file is called read var n, following the folder, following the which snapshot you want. It starts from 0. So making it 0 means you read the var 0 file for each processor. So it returns, this is called an association object. So how it works is if I give it a name, then I can use those keys to extract the values. If I want the time, I say string t. I can also put dx. I can put uu1. It returns a big list and so on. You can check all the keys in this variable using keys, and you have all those things you need. In IDL, you have those called magic variables. For example, you want to compute a magnetic field from the magnetic vector potential. That can be due when you're reading the var file.
This will also work for any IO. Will it work with collect also for HDF5 and things like that?
Yeah. You mean this function?
This,
You
yeah,
mean,
read,
the magic
that
variable?
one where you said read var files IO dist. Yeah, that one.
Yes, I would also talk about HDF5. Actually, it's yeah. Right, then the magic variables, to do that, you simply put a third argument here, which is a list, and you put in the thing you need. Say if I want the B field and I also want the current density, I do this. Then it will compute all those magic variables like BB1 and so on. So this is computed by taking the curl of the vector potential. You can also do trimming. So by default, it does not trim any ghost zones, but you can say ltrim goes to true. Then this will remove all the ghost zones. Or you can do even more. You say more. If you say more, it will remove double the ghost zones. So instead of remove 3 on each side, you remove 6. So let's say we do true. Okay, and we check, let's say UU1. So we have a really long list. Its length is this, which is actually the resolution. So 16 by 16 by 16. Sorry, should I say this? So then how do I know the XYZ coordinates of each point? Well, you just say, if you say X, it returns also a list of the same length. And it's a one-on-one correspondence between the field value and the X coordinate. And similarly, you can also say Y or Z, same thing. So then this is a short block which formulates this data variable, which is a long list. Each of it is X, Y, Z, and the field value, X, Y, Z, field value, and so on. And its length is, again, 4096. And then you can use some built-in functions of Mathematica to visualize this data. So if I use a density plot 3D, this is something I get. And you can also change the opacity and so on to visualize like places with strong field strength and so on. And of course, there are also very handy built-in functions like those ones. This will show you automatically the center planes in the box or the back planes of the box in a contour plot, or this is showing the 3D contour plot. So those are all built in Mathematica. Another thing in the package is called show slice. It takes in the returning of the read var function. You specify which field you want to visualize, and you specify which plane. So in this case, I'm saying I want to see the plane at z equals 0. So if you do this, it will show you the slice which is closest to the position you specify. If I say 100, it will only show me at z equals pi, of course. Another thing is called show slice vector. So this will show you the in-plane vector as a vector plot and the out-of-plane component as a density plot. So something like this. This is showing, I guess, density, BZ in density plot and BX and BY in those small arrows. Right, so this is just an example showing you, so you can store the magnetic field as an auxiliary variable in the F array, or you can compute it from the vector potential. So I'm just comparing those two methods. And for the auxiliary variable, you don't have the ghost zones, so it's just showing 0. But for this computed magnetic field, I'm filling the ghost zones assuming periodic boundary condition. So it also warns you that ghost zones are assuming boundary conditions, and you see they agree. So here, this is an example of 256 CPUs with 128 resolution. So I'm just using this example to show you the basic time you need to read the var file. So it takes 15 seconds or so to read a simulation in this scale. So hopefully it's not too much time. Yeah. All right. So next, reading HDF5 files. I actually succeeded to use HDF5 only from last Friday after Johannes' excellent presentation. So now I'm able to compile and run with IO HDF5. Reading those files are extremely simple, actually. All you need to say is import. Import is a built-in function of Mathematica. You say sim, and basically you specify which file you want to read. So for example, I want to read the grid file. And it returns a list of strings, actually. Those are elements in this HDF5 file. Let's say we want the LX information. So we just then give it a second argument. Oh, sorry, the Mathematica just quit unexpectedly. Okay. Go back. Here, right. Yes, so I just say import. We see those lists. And if I give it a second argument, it will read this element, which is 2pi here. And you can read all the elements at once. If you say data, it will read all the elements and return as an association object, just like we had before. So if I say var equals this, I can again extract all the elements in this way. Then you can, of course, import the var files in the same way. If you say var 0 instead of grid, then you have the var 0. And if I want, say, let's see, is there any UUX? Aha, right. Let's say vector potential AX. So I say AX. It gives, of course, a really long list. Actually, a 3D list. So 22, because this is a 16 resolution. So 16 plus 6 ghost zones is 22. So it's 22 by 22 by 22. So I don't have any specific functions to read those HDF5 files. It's already straightforward enough to just use the import, I think. I also have some very primitive functions for particles. For example, the stalker particles. So this is the command is read stalker and stalker head. So if I do this, oops, I didn't define this. And then I say this. It reads the particle files. So data. Again, this is a very huge list. I think this one of them is time, and one of them is, I think 14 is like the fields that is on each stalker particle, and 51 is perhaps the time. And on the other hand, head shows you all the field values you can read from those particles. The first three is the position. Those are the flow velocity, sorry, the particle velocity, then the flow velocity, density, and the magnetic fields. So this small block of commands is just to make 3D plots of those particles, and then I say list animate. So then you can visualize the motion of those particles in the box. Right, then some other stuffs. For example, PC functions. If you do this, it will list all the available functions in this package. Something I didn't talk about is the test field method functions. And you can check these out if you do those simulations. Another thing is called PC parallelize. This will load, so Mathematica, you can actually do parallel computations on like 4 cores simultaneously on your laptop, but you need to load the package on each of those kernels. And this is the command to do that. If I say PC parallelize 2, it will launch 2 kernels and load the package on each of the kernels. This will be useful if you do some heavy post-processing. If you are working on supercomputers, you can use those. And also there are some private functions which you cannot easily access, but in principle you can. If you specify its full name, that is by specifying all the contexts of this function, you can actually access the private functions in the package. For example, this one will read a single var file on a single processor, including all the ghost zones, I think. Right, work with supercomputers. Let me see. Actually, so this on Dardo, but unfortunately, for the time, Dardo, they have some issues with the Mathematica license, and I cannot run Mathematica now on the supercomputer. But I can show you what we can do. So basically, you need to load the Mathematica module. So on Dardo, I say module load PDC, and then I say module load Mathematica. And then I can do Mathematica. I can say Wolfram, which is the command line interface of Mathematica. Of course, if I say this now, it says I don't have the license. So, but basically, that's the way you do it. And you can also do scripts on supercomputers. For example, this is one script I have been used. So in the head, you specify where Mathematica is on your machine, and you say minus script, meaning you want it to run in the script mode. And then you just write essentially the same thing as you do in a Mathematica notebook. So here I'm reading a file from 4,000 CPUs, combine them, do some post-processing, and then output a single file. So this I write in the script, and I can say Wolfram script. So I say Wolfram script, the file. This will run it in a script mode. But of course now I cannot do it because there is some license-related problem. Right, and you can also submit it as a job. So let's say this one. So if you were at my talk on last Wednesday about correlation times, this is actually the script which computes the correlation times. So it computes maybe 10,000. So because it's done in the Fourier space, there are about 10,000 modes. You need to compute the autocorrelation functions for each of them and then fit for the correlation time. The output is, of course, relatively small because you only need one number for each mode, but during the process, it's really, it eats a lot of memory, which in principle can be done on my laptop, but it takes 1 hour or so. So then I choose to do it on the supercomputer. So I say I need 4 kernels because I have 4 runs. I want to run each of them on a single CPU. And I just then write whatever I need, some long script, and I write and I then write a job script. I need 4 CPUs, I say. I need 3 hours, and I just load PDC, load Mathematica, and I say Wolfram script the script. This is my job script, and then I just submit this job script, and it will run on the
5 minutes
for 1 hour or so.
You have 5 minutes.
So this is basically how you can do it on clusters. But of course, one issue is not every supercomputer installs Mathematica. That's something unfortunate.
Honzhe, you have 5 minutes.
There's also this small section talking about read and output data. For example, if you want to write your own functions in a package, very likely you are going to read binary files generated by the pencil code. For example, var files are binary files. So the way to do it is to use binary read, and you then specify the type of the data. In this case, let's say file is this, and I say read binary read. And the binary files, the unformatted data generated by Fortran, it started with an integer which specifies how many elements are there following this integer. So this simply means I have this many of bytes data in the file in this file, and next I do the same thing, but now I read real 32 because this is a single precision run. I do this.
Yes, we can hear you clearly.
Yeah, I wanted to say you have 5 minutes.
UX, and I do this again. I read the next data point and so on until you reach the end of the file. So this is how you deal with binary files in Mathematica. Let's say close file. Okay, 5 minutes. Let's see. I don't have so much left, so I think I can do it. So yeah, then some basic things about exporting the data. So for example, I generate a 100 by 100 matrix of random numbers. I can then export it as a .dat file like this, and then you can import this same file using import. So this will return the same nested list. Right. Another thing you can do, you can say dump save the data. So in this way, instead of outputting those numbers, it actually saves this variable. So what that means is, if now I clear that variable, so I don't have anything stored in this variable, and now I say get this dump file, automatically it will load this variable data, and I get back my data. So there are two advantages of using this dump save. One is this .m file is in binary format, so it saves some space. And secondly, it can also store functions. Actually, if your data is not a data, but actually some functions, you can do it in the same way. And it will reload this variable and you get your function back, which is sometimes handy if you do analytical theories. And of course, you can export the data in HDF5 format, which is also a binary format, and it relatively it actually has the same size as the .m file, whereas if you do it in the .dat file, it's somewhat larger. Right, and finally, you can also actually run shell commands inside the Mathematica notebook. So basically, if you do run following a string, which is your shell command, you can actually do it, and you can run a simulation even in the notebook. So if I do this, so it will return the exit code of your command, so 0 here. But if you actually print the file, you will see we have successfully sourced the pencil code, and you can actually run a simulation for using other commands. Yeah, that's basically what I have today, and welcome questions.